All right, welcome back. As promised, we're going to delve into some of the assumptions of our model and draw some examples of when those assumptions hold and when they don't hold. So, some of these are pretty easy to understand, others are a little bit more challenging. I think one of the easier ones to understand is this linearity assumption. And so, what we're going to use to check that is our scatter plot that we were using before. And so this is pretty easy. As long as there's no curved pattern at all, then this would kind of count. You might draw something that has a little bit stronger of a correlation. So this would kind of count as well. As long as there's no curvature, you're good to go. An example where this might not hold is if there's any kind of strong curved pattern in your scatter plot. And so maybe you've got data like this, where you kind of see that there's obviously this curved pattern, and if you fit a linear line through this data, it would be something like that. And that's obviously just kind of not right. And so the model assumes that the relationship between y and x is linear and that there's no curvature, at least for now. We'll get into a model that can allow for this a little bit later. The second assumption, so I'm going to go ahead and number these, is constant variance. And so for this, we're checking whether the variance of the response changes as the value of any of the predictors change. And for now, we just have one predictor. And so what we're going to use here is our residual plot that we just outlined in the previous video. And so an example where this would hold is anything that as you're moving from left to right on this plot, you're going to see that the variance of the residuals, which is kind of measured vertically, that it doesn't kind of increase or decrease as you're moving across. So for here, because these lines are pretty flat, you're good to go. An example where this doesn't hold, we'll draw kind of the most common one. Is something where you'll kind of see that the variance changes as you go from left to right on your residual plot. So in this case, when you have small fitted values, the variance is very, very small. But as you kind of go and move off to the right, your variability gets bigger and bigger and bigger. And so it's this kind of funnel shape where this constant variance assumption doesn't hold. You might also get something something that's kind of like a funnel shape on both sides. So you might have like really high variability at the beginning and then low variability in the middle and then really high variability at the end again. And so this also wouldn't hold because your variability is so small in this middle region of the graph. For both of these, we're looking at really obvious deviations from the assumption. And so we'll do a little bit of a game to kind of train our eyes and practice identifying when the assumptions hold and when they don't. The third assumption is independence. And so this is assumption about the errors being independent of each other, not the variables necessarily, just that the observations or the errors are completely independent. Another way of wording this is that one point falling above or below a line has no influence on another point. And so for this, there is no graph that we could check. I guess I'll add in most circumstances, there are special settings where we would be able to check a graph, but usually we can't check a graph, we just have to think about how the data was collected. And so I think it's a little bit easier to think of an example where this doesn't hold. And I think the most common setting in simple linear regression for this not to hold is if your explanatory is time. And so you could kind of think about maybe measuring, using time as your explanatory variable, and then using, say, I guess, temperature as your response. So outdoor temperature maybe in Canton, New York. And so what typically happens with temperature is that it kind of goes through cycles, at least here, where it'll be really cold for a few days, but then it'll warm up a little bit, using the term warm relatively this time of year. But you might have some days where like it's freezing cold and it stays cold, but then it kind of warms up, and then it's kind of cold again. And so this also kind of violates the linearity assumption the way I've drawn it, but the idea is that if you kind of fit this graph, if you know that this point falls below the line, then you have some idea that the next point is also going to fall below the line as well. And so the observations are not independent because they're correlated through time. And so we'll just kind of write that first part out. So knowing that this point falls below the line tells us information about other points. In particular, these surrounding points are kind of more likely to fall below the line. So they're not, these observations aren't completely independent. We'll talk more about this assumption too. I think independence is the hardest one to kind of get our heads around, mainly I think because there's not always a simple kind of graphical check. You really have to think about where the data is coming from. And so assumption number 4, I think, is pretty easy. So we could go back and do an easy one, which is kind of nice. Normality, just that the errors are normally distributed. And so we're going to check our residual or our histogram of residuals to make sure that there's not any extreme skewness there. And so an example where this assumption would hold would maybe be something like, gosh, I don't know. We're just looking again for extreme skewness. So this is probably still fine. It's like slightly right skewed, but it's pretty much good to go. Something where it wouldn't hold might be something like this. And so here we're seeing that the residuals are very, very skewed. And so that is, that's an issue for our model, mainly for constructing prediction intervals, which we haven't really talked much about yet. But again, this one's pretty easy to check. And usually this one is kind of the least important of the assumptions, and that if it's violated, most things still tend to work, which is good. The last assumption is randomness. And so that's this idea that the data is generated by some sort of random sampling or a random experiment. If that's not the case, then we kind of have to think a little bit harder about our scope of inference, meaning what population we can extend the results of our regression model to. Um, and so an example, kind of using something that we did before with the GPA in Stat 213, you could kind of argue that it doesn't really hold in that setting because students in spring 2020 are not representative of students taking this class now. And so you can make the argument that yes, you could still kind of model that data, but you shouldn't extend it to you all taking this class in spring of 2021. But you could also make the argument that maybe they aren't really that different, and so they are representative. And so, again, this one is also a little bit hard to think through. You just kind of have to think about how the data was collected and if that data is representative of some larger population. And so we're not going to really do an example where the assumption holds. We're just going to make a note to ask ourselves, is the sample collected reasonably representative of some larger population? To do kind of one more example with this, with our baseball data, that was collected in 2011. And so if you were looking at the relationship between runs scored and at-bat percentage today, you might think that that 2011 data is pretty reasonably representative. Because I mean, I'm not super into baseball, but not that much has changed in the last 10 years. On the other hand, if you were trying to make your scope of inference to baseball in 1930, then that's a lot more questionable. And so you might not be able to kind of extend your conclusion to baseball games played way back in 1930 without some other strong argument outside of statistics.